actually want to talk about the convolutional part of a convolutional neural network, or CNN, which is what it's called, just because it's easier to say. So in a CNN, what makes it more different from just a traditional neural network is how the data is formatted. So we talked in the previous lesson about input layers and how you're just passing an image and the label, but we can actually make the image show a lot more than it traditionally would have. And that's where the idea of convolutions and kernels comes into play. And so let me actually go back to the Google Colab, the Jamboard, which has a good GIF on it real quick. 1 second. You saw a little bit of the other lessons, but essentially, here's what a convolution looks like at the end of the day. You have the image, you have like a kernel. You know what, let me just explain what a kernel is. A kernel is this moving filter you see. So you see how there's like a 3x3 dark box right over here, and you can see how it's moving across the image. So the image is the big blue thing right here. The image, let's just say that's like, a 5x5 image. That's the actual image that we're working with, right? So we're looking, this is kind of in like the data formatting phase of a neural network, of a convolutional neural network. So we say this is a 5x5 image, and then pretty much all we need to know about this image for the sake of this exercise. So what's happening is just that this kernel is going across each part of the image. And we want to actually, we're trying to extract some meaning from it. But what we do is that a convolution, at the end of the day, it's what's called a filter. So if you've used Snapchat or Instagram before, you've seen what filters do, right? You can have different kinds of sunlight, different kinds of brightness, etc. And a convolution is the same idea. And so let's just say, for example, that a convolutional filter is the kind of function we're applying. And so here's like basically a math example of it. You guys don't really need to know this part, but essentially, let's say the image, it's a pixel. So this is the pixel representation of the image, right? 2 to 2, we have like a 3 in there, but the kernel is a 3x3 kernel. And so the kernel is just basically what you want to think about when thinking of a kernel is that the kernel is the moving box, but a convolution is the actual function inside of that box. And so the numbers you see in here is the convolution, and the box is the kernel. And so that's what's going on. Basically, we multiply this convolutional filter onto the image and we get a certain output. And so what does that actually mean? So if we look right here, let's just put some examples in. Let's say that the filter is going to be, just as an example, something like, let's say the filter just multiplies each pixel by the number 2. Actually, it has to be some kind of a matrix. And so let's just say that it's going to be a matrix that just inverts the image. And so let's just call it matrix Z. 1 second. Some matrix Z that inverts the pixels that we have. And so when we multiply matrix Z, which is, let's say matrix Z is held in these dark, you see the dark box moving? Let's say that matrix Z is in that dark box. When it's moving across this blue image, we're multiplying matrix Z by the data that we have in that subset of the image. And so, for example, we have this 3x3 section right here. We're going to multiply matrix Z by that area, and we're going to get a corresponding value with it. And so let's say that we get this value to be 1 when we multiply it by those pixels, and then we do it for the next section. We're going to get 2, might get 1 again, we might get 0, 1. I'm just making up values. Another 2, maybe a 3, maybe a 4, and then maybe like a 9. So we end up getting this new set of values from this image that may not be what we saw before. And so when we apply this filter, right, we have this 3x3 kernel moving across it, and it's applying this filter to it, then we get a very, very different kind of data that we might have not got before. And so if we think about having like a picture of a tulip, right, in this blue box, right, and we apply like some kind of filter that maybe increases the brightness, then maybe we see things like the petal. The petal stands out brightly. Let me give you guys an example. If I go to the next frame here, right, we have this filter here. So this is a 3x3 filter. Sorry about the zoom. 3x3 filter. And then when you actually multiply it by the picture of a cat, so you actually will obviously have to convert this to pixel format before you do, the matrix multiplication. But once you convert to the pixel format and you multiply it, then you're going to get these contours, right? And so this is a very, very different image. You're applying this filter. You can see this is almost like a contour filter. Contour basically means lines. You can see, oh, if I'm a model, if I'm a neural network, now I'm starting to see much more meaningful features of the cat. Oh, like I see these ears. Oh, I see these paws. I see these paws. I see these whiskers. I see the eye. And you see a lot more than you would have seen just by, instead of just looking at this picture. And so when you have different types of convolutions, you get a lot more extracted from your data. And that's the first step of what makes a convolutional neural network so powerful. Instead of just passing that raw data, you're getting more meaningful data. And I'll talk about next steps if I can actually minimize this data or even get better results in the next lesson. Thanks for watching.